Okay, so let's get cracking. The first thing I want to do, I want to derive an identity that I'm going to use a lot in what follows, okay? It's an identity that I think that you know, but let's just rederive it and make sure that it's uppermost in your mind. So imagine that we want to evaluate the following integral. We'll have an integral d4x. We have f mu d mu g. So I'm going to rewrite this as follows. I'm going to write this as an integral d4x, and then I will have d mu f mu multiplied by g, and then I will have minus d mu f mu g. So you've seen me do manipulations like this many times before, but let's just talk through it. So look at the right-hand side. The first term in the integrand on the right-hand side, I've got a d mu acting on f mu g. So I should use the product rule. And the product rule will produce two contributions. So the first contribution is when d mu acts on f mu, and then I just multiply it by g. That first contribution is going to cancel against the minus d mu f mu times g. There's a second contribution from the product rule, which tells me I have f mu onto d mu g, and that agrees with the term on the left-hand side. Okay? So the product rule produces two terms. One cancels against the negative term on the right-hand side, and the remaining term is equal to the term on the left-hand side. So you've seen manipulations like this before. The next thing that I want to do, again, something that you've seen me do many times, is to cross off this term over here. Why can I cross it off? And you should immediately know, well, this is a boundary term. So that's a boundary term. And then what do we land up with? Well, we've got minus the integral d4x d mu f mu and then g. So what I want you to notice here, look what we've done, what our identity says. Look at the first expression and the last expression. So I'm reading here and here. It tells me I can take the derivative of the g, flip it onto the f, but that costs me a minus sign. So I'm going to want to use that identity again and again and again. Okay, so now let's get started with our derivation. So what did we do? Okay, so I want you to remember what we did for the one-dimensional integral. So when we started off trying to evaluate I of b, we shifted x. And how much did we shift x by? Well, it depended on where the exponent peaked. Where did the integrand peak? So I want to repeat exactly the same calculation. So I'm going to look at z of j, and I'm going to ask, where does that exponential peak? So where is the exponent at its extremum? So let's just do that. So I'll just put down, where does exponent of z of j peak? And I hope you know that it's slightly sloppy. It's the exponent of the integrand of z of j. Where does that peak? But I just writing it there to remind you of what we're doing. So we'll have delta phi of x. Remember, for the 1D integral, we took the phase, which was minus alpha over 2x squared plus b of x, and we differentiated with respect to x, set that equal to 0. Now our exponent is is plus integral d4xj of x phi of x, and we are integrating with respect to phi of y. So we should take a derivative with respect to phi of x, that's the integration variable, and we should differentiate the exponent, that's is plus the integral. I'm going to say d4y, because I don't want to mix up my integration variable with the x inside the phi of x. And then I've got j of y, phi of y, and I want this to be 0. That's where this exponent is going to peak. So let's just see exactly what we're calculating. So we've got delta phi of x. Then we've got I. Let's plug in the action. Again, d4y, because I don't want to mix the variables up. Then I'll have 1/2 d mu phi of y, d mu phi of y, minus 1/2 m squared phi squared of y. And then we'll have an integral d4y, j of y, phi of y. Good. So that's the derivative of the exponent. Let's just evaluate it. So we'll have I integral d4y. Now we can hit this first phi field. So we'll have a d mu, and then we'll have a 4-dimensional delta of x minus y. There's the second phi of y. Oh, sorry. That second phi of y is different. We've got the derivative of it. So we should have a d mu phi of y. And then we'll have plus, and now we can differentiate the second phi of y. And again, we get a 4D Dirac delta. And then we've got minus, if we differentiate the phi squared, we'll get 2, so that'll cancel the 1/2. So we'll have m squared phi of y times by a delta of 4 x minus y. Good. That's from the first term. And then we've also got plus an integral d4y. We'll have j of y. And then we'll have delta of 4 x minus y. Very good. Now what I want to do, I want to use the identity that we derived. So I want to flip the derivative over. So for the first term, I'm going to flip the derivative from the Dirac delta onto the field phi. And from the second term, I'm going to flip the derivative from the Dirac delta onto the field phi. And you can see that these two terms then give exactly the same contribution. So I'll have an I integral d4y. I'll add the two contributions, so the half will go. I need a minus because that's what our identity tells me. When I flip the derivative over, it costs me a minus. I've got a delta 4 x minus y, and now both derivatives act on my field phi because I have flipped the derivative over. Then for the m squared term, well, I can do that integral because integrating with the Dirac delta is particularly easy. So I'll have a minus, I'll have an I, m squared, and the phi of y becomes phi of x. Good. That looks fine. And then for the last term, I can also do the integral, and I just get j of x. Now for the term that I've got here, the one integration term I've got left, well, easy to do that integral, again, thanks to the delta. So I'll have minus I d mu phi of x minus I m squared phi of x plus j of x. Okay. If you solve this equation, so, and this is of course equal to 0, if you solve this, you will get the value of phi of x. So you're solving for phi of x that maximizes the exponent of the integrand of z of j. And this is just like what we did in the 1D problem. We maximized the exponent, and then that told us how much we should shift by. So call this solution phi naught of x. So phi naught of x will solve this equation. So we'd have minus I d mu phi naught of x minus I m squared phi naught of x plus j of x is equal to 0. And I'm going to simplify this a little bit. I can write this as d mu plus m squared phi naught of x. There's a minus I multiplying, but I can get rid of that minus I by multiplying by I. I'm going to take j of x to the other side. That'll make it negative. I've multiplied by I, so I'll get minus I j of x. So this equation here, this is the equation that tells me where the exponent of the integrand of z of j peaks. And this is what's going to tell me how much I have to shift phi of x by to make phi of x look like z of naught. So that's the logic. Go back to our 1D problem and make sure that you understand that logic perfectly, because I'm just repeating that logic again.